H5502 Unit 3 Acid Hydrolysis of Octahedral Complexes. I am Dr. Devang Pandya from Department of Chemistry, St. Xavier's College Autonomous, Ahmedabad. Well, in previous lecture we have discussed regarding the different type of hybridization in octahedral ligand displacement reaction, and there should be one query raised by a few students about the difference in the energy of the intermediate when the reaction undergo dissociation or association mechanism. So let's see what is the difference between these two. See, actually there is very minor difference to distinguish whether the reaction undergo SN1 mechanism or whether the reaction undergo SN2 mechanism. Here we have given you two different diagrams for this, and the other one is the third one as well. Now dissociative, that is SN1 mechanism, in which you can see here this is the complex and this is the attacking nucleophile. When nucleophile is going to attack, it has little stability and then it goes up and then it's going to give us a product. As far as the rate of reaction is concerned, the rate of reaction, when we see, it is always depend only on the substrate, yani main complex, and that is why it is considered as unimolecular first order ligand substitution reaction. On the other hand, when we have associative mechanism, you can see compared to this one, the graph looks as if it is similar. As already I've told you, very minor differences there in the reaction. You can see the energy and heat of reaction as well. Very minor differences there between the dissociative or associative mechanism. But here when we go through this associative reaction mechanism, along with the concentration of the main substrate, the concentration of the nucleophiles will going to affect the reaction, and as a result of that, when the reaction take place, it goes up to achieve the activation energy, and in the intermediate it has little stability and then it goes down. So when the reaction transits between dissociative to associative, or maybe if we do not found the intermediate during the reaction, then the process will undergo interchange associative, whether interchange dissociative mechanism. So here you can see that the reaction will take place and there is no evidence of intermediate in the excited state, and as a result we are going to get only one hump. So as far as dissociative is concerned, we have a little stability for the intermediate, so that the presence of intermediate can be obtained through spectroscopical tools using during the progress of the reaction. On the other hand, associative mechanism, yes, there is a presence of intermediate, and you can notice the pentagonal bipyramidal intermediate coordinated 7 over here. But when there is no evidence of intermediate, we're going to get this kind of energy profile diagram. So this is what there is a clarity in this the difference between SN1 SN2 mechanism and whether it undergo interchange associative or dissociative mechanism as well. Now a broad way of the classification of this ligand substitution reaction, we can classify reaction into three groups based on their stoichiometric mechanism. First one is the associative, which involves the intermediate of increased coordination number, that is from coordination number 6 it goes to coordination number 7. Other is the dissociative, that involves the intermediate of decreased coordination number, and in both the cases there is evidence of the intermediate. And the third one is interchange, where there is no evidence of any intermediate during the progress of the reaction. Likewise, we can divide the intimate mechanism into two classes. If the interchange will be there and if there is no evidence of intermediate, it may be either referred as small a instead of capital A. Will have small a. Rate is affected by the entering group, so it is interchange associative mechanism. And B, that is dissociative, rate is affected by leaving group, so it is interchange dissociative, that means ID mechanism. So that way we can classify this reaction mechanism. Overall, this gives us 4 limiting cases. A classic organic description of each reaction mechanism is given in the parenthesis. One is D, that is comparable to SN1 limiting case. The other one is A, that is comparable to SN2 limiting case, and this all compared to the organic reaction. And when IA comparable to typical SN2 kind of reaction, but there is no evidence of intermediate, and ID, that is comparable to SN1 reaction, but there is no evidence of intermediate. The rate law of substitution mechanism can be classified. Rate laws for the different classes of reactions can be derived rather easily. Here are the rate laws and free diagram associated with the mechanisms that we have discussed earlier in the previous class. In the case of the IA mechanism, we could say that the bond from the increased ligand start to form before the leaving one will start to break, and that is why it is interchange associative, but there is no evidence of intermediate. But the attacking group, that is nucleophile, is going to attack with the central metal ion before the leaving group break. It means that when attacking group try to come closer to the central metal ion, leaving group depart. That means the bond length between metal and leaving group get increased when a nucleophile will attack on the central metal ion. This kind of case is there where it is considered as IA mechanism, interchange associative mechanism, and in this mechanism there is no evidence of any intermediate. On the other hand, if we have ID mechanism, we could say that the exiting group or leaving group from the metal ligand bond start to lengthen, weaken. The bond length of the metal and leaving group increase first before the nucleophile will attack, and that is why it is called interchange dissociative mechanism. Means leaving group depart first and then attacking group will going to attack. So that way we can bifurcate the reaction mechanism in the ligand substitution reaction in octahedral geometry. A pure interchange would have the leaving ligand metal bond weaken at the same time that the incoming metal ligand bond forms. So that is considered as purely interchange mechanism. Now, point to discuss in today's lecture. This is about the previous lecture and your queries. And now, point to discuss regarding today's lecture. We are going to discuss hydrolysis, acid hydrolysis, factors affecting acid hydrolysis, and the reaction without metal ligand bond cleavage. That is also a hydrolysis reaction without metal ligand cleavage that we are going to study today. Now, hydrolysis. The rate of reaction gives misinterpretation of the mechanism of the reaction, but substitution reaction in aqueous solution is found to be accelerated by the presence of an acid or base. The pH of the solution is the deciding factor for the product in the hydrolysis reaction. Water containing complex is obtained in acidic solution, say for example pH lower than 3, while the hydroxo complex is going to be obtained in basic solution while pH would be greater than 10. If the hydrolysis take place at pH less than 3 and we will going to get an aqua complex in the product, then it is considered as an acid hydrolysis. And if we are going to get the hydroxo complex in the product and the reaction proceed at pH higher than 10, then that hydrolysis is considered as base hydrolysis. But today we are going to discuss maximum about acid hydrolysis in the octahedral ligand substitution or replacement reaction. So in this hydrolysis reaction in which ligand is replaced by a water molecule or a hydroxide group. But when we discuss regarding acid hydrolysis, the ligand in the complex, substrate complex, is substituted by only water molecule and aqua complex is going to be formed. So the reaction in which the water molecule replaces coordinated ligand from the complex and species in aqueous medium is termed as equation reaction or acid hydrolysis. This is, see student, this is another name of acid hydrolysis, that is equation reaction. Acid hydrolysis is always termed as equation reaction. So if somebody will ask you explain equation reaction with mechanism or acid hydrolysis with mechanism, you need to explain the same thing. Example is given over here, that is pentamino chloro cobalt plus 2 complex and its reaction with aqua molecule, that is hydrolysis at pH lower than 3, we're going to get mono aqua pentamine cobalt plus 3 complex. Chlorine is get substituted during the reaction and oxidation state increase from +2 to +3. That you need to keep into mind. Another example here is this A would be any spectator ligand you can take, and therefore alphabetical A is used. Chlorine ethylene diamine. So ethylene diamine is a chelating complex with cobalt, and we are going to substitute one of the chlorine from this complex here for +1 oxidation state, and that increase to +2 when ligand chloride is substituted by water molecule at pH lower than 3. So these are both the example of acid hydrolysis. Base hydrolysis reaction may be defined as the reaction in which a hydroxyl complex is formed due to the replacement of ligand by hydroxyl ion, and base hydrolysis reaction occur in solution having pH greater than 10. Considering we can get the different kind of reaction over here. This is the base hydrolysis reaction. You can see ligand chloride is substituted by hydroxide ion and we're going to get hydroxyl complex, and this reaction undergo at pH greater than 10, and as a result it is considered as base hydrolysis. Equation or acid hydrolysis reaction of hexa-coordinated cobalt 3 amine complex. This is this example, specified example for this equation or acid hydrolysis reaction. It is not limited though up to this cobalt hexamine cobalt complex. You can take many example for the hydrolysis, but here to explain the mechanism and the factors affecting acid hydrolysis, we have specified the example of hexa-coordinated cobalt amino complex. So we have pentamino monochlorocobalt complex, and it undergo reaction with aqua ligand. So one of the chloride gets substituted by water molecule pH below 3, and that is why it is considered as acid hydrolysis. The rate of reaction is counted as constant K into concentration of the main substrate, that is pentamino chloride plus 2 complex, and the concentration of the attacking nucleophile, that is water molecule. But when we see that in this compound water molecule, if we are going to take, that is in excess amount, its mole value would be 55.5, and very less water, only 1 mole water going to substitute chloride. That means there is no major change in the concentration of this one. Hence we can consider the reaction may alter through the concentration of the substrate only. There is no effect of the water molecule over here. As a result, it is looks as if it is SN1 kind, or we can say unimolecular first order, pseudo first order reaction kind of reaction study we can obtain from this rate of reaction. Rate of reaction would be dependent only on the concentration of the main substrate, not on the concentration of water. You can see that water molecule from 55.5 mole, only 1 mole, hardly a part of water is used to substitute chloride in the complex. The rate alone does not indicate whether this reaction proceed by SN1 dissociative mechanism or followed by addition of water, or by SN2 displacement of Cl by H2O. SN2 mechanism or SN1 cannot be decided based on only the rate of reaction. There are so many factors which going to affect this substitution or displacement reaction. We need to go through each factors affecting this hydrolysis. Then and then we are able to say whether the acid hydrolysis will undergo SN1 mechanism or SN2 mechanism. So we need to study different factors affecting acid hydrolysis. The nature of mechanism depends on the following factors. First is effect of the charge on the complex. If the charge is more, if the charge is less, the mechanism will going to get changed, or either the rate of reaction either increase or decrease depending on the charge of the complex. Other one is the inductive effect of the inert group. Inert group, that is a spectator ligand which is already there with the central metal ion but will not participate in ligand substitution reaction, but they may alter the rate of reaction as well. The chelation, if there is a chelating ligand, then there should be a steric hindrance, so attacking nucleophile will not going to attack the central metal ion that much easily, and that is that way the chelation may alter the rate of reaction of this hydrolysis, acid hydrolysis. Another factor is the effect of substitution on ethylene diamine. After chelation, if we have a chelating agent like ethylene diamine, and the hydrogen of ethylene group, if substituted by more functional groups and make the ethylene diamine a bulkier substituted group, then the rate of reaction may get altered through the in the reaction mechanism of this acid hydrolysis. Another factor, that is effect of leaving group or the basicity of the leaving group, or we can say the nature of leaving group, may alter the acid hydrolysis as well. And finally the solvation effect as well. So solvation effect is the another effect which may affect the ligand substitution reaction as well. So these are the factors affecting the ligand substitution reaction in acid hydrolysis of octahedral complex. Let us discuss regarding the solvation effect first, because as soon as we take the compound, we add into water or another kind of solvent, and therefore solvent is a factor which affect the ligand substitution reaction in the acid hydrolysis as well. So according to the solvation theory, in aqueous medium, the reacting complex, the intermediate formed, and the product obtained are all in the hydrated state. The hydrated state of a species is represented by putting the subscript HYD or AQ in the species, which you know that during the reaction we will write AQ in a subscript. Let us compare the rate of equation of complex pentaamino cobalt plus 2 and ethylene diamine triamino chloride cobalt plus 2 complex, which is a smaller in size than the complex 2. Since complex 1, that is pentaamino cobalt chloride, is bigger in size, has only monodentate ligand, while complex 2, that is ethylene diamine triamino monochloro cobalt plus 2 complex, has chelated as well as monodentate ligand associated with it. If the equation of the complex is assumed to proceed through SN1 mechanism, the equation of this complex can be represented as the example which is given earlier, that is the chloride substituted by water molecule. But in the both cases, when we go through this, we found that the rate of reaction is more faster if we have less crowdy group associated with the central metal ion. So if we want to study the solvation effect, we need to study all these effects, and hence we can understand how solvation effect will be altered by this factor as well. And that is why I haven't shown you the example of solvation over here. Let us discuss the first one, the effect of the charge on the complex. In an increase in the positive charge on the complex species decrease its rate of acid hydrolysis. That means more the charge on the complex, lesser the reaction, slower the reaction would be. The decrease in reaction rate is observed as the charge of the complex increases. A dissociative nucleophilic substitution seems to be operative. Means if the charge is high, the acid hydrolysis undergo mostly SN1 kind of mechanism. How it is? Let's see with the example. The acid hydrolysis here, which going to replace one chloride ion by one aqua molecule, will proceed in two steps. First step is the faster one, where when we introduce aqua ligand with the substrate, chlorine is going to be substituted. One of the chlorine is going to be substituted, and when the chlorine is substituted, the oxidation state, you can see over here, the oxidation state, which is +1 in the reactant side, increase to +2, and then the red deciding step is this one. The +2 oxidation state is there, and it will going to substitute another chloride, and we're going to get the aqua complex where oxidation state increase to +3. So here we have two reactions to compare. One where we have lower oxidation state, you can see reaction is fast. When we have higher oxidation state, reaction is going to be little slow. Now and because this is intermediate, this happens. We will compare this with the other example as well. In the case of the charge on the complex would make the breaking of metal chloride bond more difficult, hence the rate of reaction decreases. However, if it takes place through SN2 mechanism, the rate of reaction should practically unchanged with any kind of change in the charge of the substrate. But here we notice the change, and that is why we can say that it won't go under SN1 mechanism. Now, inductive effect of the inert group, or we can say spectator ligand, which is already present in the complex. Our example is we have ethylene diamine, 2 molecule will going to chelate the cobalt ion. We have pyridine, and that pyridine is substituted by any ligand A. Which ligand A is there? We're going to change this ligand A, and we'll find out what happened in the process, in the mechanistic process of this ligand substitution reaction. The rate constant of acid hydrolysis reaction increase with the methyl group substitution in pyridine. That means if one hydrogen of pyridine is substituted by one methyl group, then 2 methyl group and 3 methyl group. As the number of methyl group increases over here, there should be a change or increase in the acid hydrolysis. That means if instead of A will put one methyl group, its rate of reaction is increased little bit. If I put 2 methyl group over here, rate of reaction even increase than the previous one. So that way rate of reaction increases. A substituted pyridine is an inert ligand, where A is the substituent group like methyl group. So that is monomethyl pyridine. A pyridine means monomethyl pyridine. The increase in the rate of reaction is due to the inductive effect caused by the increasing methyl substitution, which result in distorting the electron density towards the cobalt atom, and thus helps the dissociation of chloride. So that way chlorine dissociation takes place rapidly. As a result, the rate of hydrolysis, acid hydrolysis, increase if we have more substituent group on pyridine. This again confirms the fact that acid hydrolysis undergo SN1 mechanism, not SN2. Value of rate constant we can see here: 1 methyl group 1.1 into 10 raised to -5, 3 methyl group in the pyridine, then 1.3. That means the rate of reaction increased. And if 4 methyl group is there with pyridine, you can see it increase again. So more the substituent group, because of its inductive effect, the electron density reach to cobalt, and cobalt chloride ion become more labile. The length between metal and chloride increase, the bond become weak, and ligand substitution of chlorine become more effective. As a result, rate of acid hydrolysis increased, and it indicates that dissociation takes place first before the nucleophile will attack, and as a result we can say that this reaction will facilitate SN1 mechanism rather than SN2 mechanism. Now, effect of chelation, and the chelation, you know, it will going to create crowding near the central metal ion. As crowding increase, static effect increase as well. So here you can see that an increase in the steric crowding around the central metal ion preferably favors dissociative nucleophilic substitution, that is going to facilitate SN1 mechanism. We have the example where let us consider pentaamino cobalt chloride plus 2 complex. The ammonia molecule in this pentaamino chloride plus 2 complex ions are replaced by ethylene diamine. The rate of hydrolysis get decreased. That means a simple ligand when substituted by a chelating group, the crowding increase, steric effect increase, which decrease the rate of hydrolysis. So that is why we can say that a chelation can decrease the rate of hydrolysis. Here you can see that this is a fast reaction, and when we have introduced ethylene diamine instead of amino group over here, instead of 4 amino group, we have introduced 2 molecule of ethylene diamine, which are 2 chelating agent, and due to this chelation, crowding effect increase. Oxidation state is not going to affect, because in both the case you can see oxidation number are similar, but the crowding of ethylene diamine, a chelation of ethylene diamine with central metal ion increases, hence this reaction is going to proceed slowly, this one is going to proceed faster, but both this reaction facilitate SN1 mechanism, that you need to keep into mind. It has been observed that the chelation shorten the carbon-nitrogen bond distance in the ethylene diamine, and hence the transfer from it will transfer more charge to the central metal ion, and as a charge is shifted to central metal ion, the density electron on central metal ion get increases. This should be enhance the rate of acid hydrolysis. However, according to the solvation theory, the relative rate of acid hydrolysis of chelated complex decreases. It should increase, but it decreases, because hydration of any species decreases its energy and thus stabilize it more, and as there is more stability, the ligand substitution reaction take place in little more time, and as a result, instead of we should get a faster reaction, because the metal nitrogen bond will going to transfer the charge more on metal ion. So leaving group like which is electronegative like chloride should depart fast, but instead we're going to get the hydration when we are going to add that complex into water, or solvation theory is going to alter the things, and as a result we're going to get a decreased rate of ligand substitution reaction in acid hydrolysis on chelation. So this is a that means a little controversial statement. Chelation may increase the charge on metal, and hence the rate of hydrolysis should increase or enhance, but instead that due to solvation chelated complex acid hydrolysis decreases. Why? Because of the solvation, the relative rate of acid hydrolysis of chelated complex get decreases, as the electrodensity decrease on the central metal ion, the chlorine will not depart that much easily. So that you need to keep into mind as well. The higher the charge and the smaller the size of the complex species, result higher extent of hydration, and consequently its stabilization. For the example, we can see 2 example is here. Hydrated complex, fast ligand substitution reaction will get penta coordinated intermediate, that is also hydrated, and when it bring to the acid or lower pH with water molecule, will going to get the aqua complex. So equation reaction take place over here, but there is a simple ligand. If we have a chelating group, the reaction gets slow due to the hydration. So it should increase, but instead due to hydration, due to solvation, it get decreased and will going to get slower reaction over here. So that you need to keep into mind. The another factor in this progression in the chelation, if the intermediate like diamino ethylene diamine monoamino cobalt plus 3 complex of the chelated complex is bigger in the size than the intermediate pentaamino cobalt plus 3. In the previous reaction, you can see in the example that both are having plus 3 oxidation state, but here all the ligands are amino group. Here only one amine is there and two chelating ligand is there in the intermediate. So here we are discussing that one. So in the intermediate, you can see that both are having same oxidation state, but here the chelating group is there and here all the ligands are amino, non-chelated complex. So this one is going to be bigger in size, this one is going to be smaller in size. Hence the rate determining step of the chelated complex, that is cobalt ethylene diamine, 2 is there, 2 is missing, it is not missing, it is written as that way only. If this complex is there, mono ethylene diamine triamino monochlorocobalt plus 2 complex would be slower compared to non-chelated pentaamino monochlorocobalt plus 2. 5 is missing over here, that you need to mark. Take note of this. 5 should subscript should be over here. It is equivalent that the chelation factors can be explained with the help of dissociation SN1 mechanism. So this chelation theory also felicitate SN1 mechanism as well. Now, effect of substitution on ethylene diamine. If chelation is there, but even in the chelation, the hydrogen of the ethylene group of ethylene diamine, if substituted by another group, more bulkier group remain closer to the central metal ion. Then what happens? When hydrogen of the carbon or iron or nitrogen atom of the ethylene diamine in this bis ethylene diamine dichlorocobalt trans complex, when replaced by any alkyl group like methyl or ethyl group, the ligand become more bulkier, more crowded, more strained. As a result, the strained complex having bulkier ligand undergo SN1 dissociative mechanism. The crowding on the complex with coordination number 6 is reduced to converted into penta-coordinated intermediate. Hence, the removal of one chloride from the complex reduce the conjunction, or we can say a crowding surrounding the central metal ion, and give little stability to the intermediate, and the intermediate is less strained compared to the main substrate, and hence SN1 process is easier process, and that is assisted by the steric hindrance. So steric assistance is there, and we're going to get the SN1 process, which consists of the loss of chloride ion very rapidly. On the other hand, if the strained complex if undergo SN2 mechanism, then the hexa-coordinated will turn to hepta-coordinated. That means one more ligand is going to increase in the transition state, which increase the crowdiness of the ligand surrounding central metal ion, which can make the intermediate less stable. Hence, it is not possible that the acid hydrolysis of the crowdy ligand surrounding central metal ion should go SN2 mechanism. So that can be easily understood over here. Next is the effect of this substitution on ethylene. Thus, the transition state is more strained than the original complex, and SN2 is difficult. Already I have discussed the steric hindrance is going to increase more, and experiments have shown that the complex containing substituted diamine react more rapidly than those having simple ethylene diamine. And we can see in the table in the next slide that the rate of hydrolysis of this doubly, we can say, chelating ligand at 25 degrees centigrade at pH 1 correspond to the replacement of one chloride by H2O molecule are given. Here AA is considered as ethylene diamine, that you need to keep into mind. And from the values, it is obvious that with only one exception, the effect of the increase in the number or the size of the alkyl group substituent group in place of hydrogen to either the methyl group or amine group in ethylene diamine increase the rate of hydrolysis for the loss of chloride ion, and the increase in rate observed when more bulky ligands are used in good evidence in favor of SN1 mechanism. So this also felicitate SN1 mechanism. These are more example where either the hydrogen of the methylene group or amine group, if hydrogen that substituted by either the methyl or ethyl group and sorry, more bulkier group is going to be obtained, you can see the rate of reaction is drastically get increased, and it will felicitate SN1 mechanism. So that you need to keep into mind. Now, effect of the leaving group or the basicity of the leaving group or the nature of leaving group on the ligand substitution reaction. The rate of acid hydrolysis of penta-amino cobalt chloride complex during the replacement of one chloride with H2 molecule depend on the leaving group, that is chloride, because the rate determining step would be the bond breaking step. That you need to keep into mind in SN1 mechanism. It has been observed that the reactivity of leaving group decreases in order of the leaving group's charge, nuclear charge, since the strength of metal ligand is directly proportional to the basicity of the leaving group. The reactivity of leaving group decreases. The rate of acid hydrolysis decreases with increase in the strength of metal and leaving bond with the increase of basicity of leaving group. If the basicity get increased, metal ligand leaving group bond gets strengthened, and as a result acid hydrolysis, the rate of acid hydrolysis decreases. This indicates that the rate determining step in the acid hydrolysis involves dissociative mechanism or SN1 mechanism as well. So most of the factors we are going to advocate that SN1 is the reaction mechanism for ligand substitution reaction as far as acid hydrolysis is concerned. The rate of equation of pentaamino monohalo cobalt plus 2 corresponding to the replacement of any halide with H2O molecule depend on the nature of the halide, because the bond breaking step is important in rate determining step. As already we have discussed earlier, it has been observed experimentally that the reactivity of X decreases in this order. This is the order in which the leaving group and the reactivity of this leaving group. These are all leaving group, not halo group. These are all leaving group. X is considered as leaving group over here, and this is the way the decrease the reactivity of the complex. This order corresponds to the order of decreasing thermodynamic stability of the complex formed with these groups as well. The result of various investigations indicates that SN1 is the mechanism through which the ligand substitution reaction takes place in acid hydrolysis. Bond breaking is important in the activated complex at the end, that you need to keep into mind. So this is bond breaking and bond making process which is important. So all in all, if we see that the charge of the complex increases, if the charge on the complex increases, a rate of reaction decreases and felicitate SN1. Basicity of the leaving group increases, it decreases the rate of reaction and it will felicitate SN1. Solvation increase, then rate of reaction increases. That is the another factor. And the steric factor or chelation increases, it will decrease the rate of reaction and felicitate SN1 mechanism. Reaction without the metal ligand bond cleavage, the hydrolysis without metal ligand bond cleavage. The substitution reaction takes place without metal ligand bond cleavage is the reactions where metal ligand bond preserved after the reaction. This is the example for that. The acid will going to substitute one of the carbon monoxide from the reaction from this carbon dioxide, and we're going to get the aquaso complex. During the conversion of the carbonate amine cobalt pentaamino cobalt carbonate complex into its aqua complex, the oxygen bond breaking take place rather than cobalt oxygen bond breaking. And this observation has experimentally verified. By putting the O18 labeled isotope, we can identify that yes, the cobalt oxygen bond will not break, but it will the oxygen bond which is going to be broken during the reaction. So this is the reaction in which we have labeled the oxygen of the aqua complex, aqua ligand, by O18, and we found that O18 will be over here. It means that oxygen bond broken from the carbonate ligand. The mechanistic pathway is given over here. So this is the mechanistic pathway of the reaction. So you can see that this is the carbonate ion, and acid is going to treat with it. So acid proton is going to attach with the negatively charged oxide, and from hydroxo intermediate the proton will get shifted, and the oxygen bond is going to be broken over here from this hydroxide. After breaking this bond, carbon monoxide depart, and we're going to get one hydroxo complex over here, and that result into the final product. The mechanism proves that these type of reactions are decarboxylation reactions, and the chloro complex in pentaminochloride has been converted into its nitro complex, substituting one chloride after treating with NO2 minus. Now, this reaction does not involve cleavage of metal ligand bond because of the formation of aquo complex. So this is another example where and this may be asked in the MCQ, that you need to keep into mind as far as your CI2 is concerned. So here also ligand substitution take place by this group. Thank you for listening this lecture patiently. I always inspire you. Please keep balance between your work, your study, your job, your family, and be happy, stay safe. If you have any question and doubt, feel free to ask anything in the chat box, either in the mailbox.